let's take another look at mass spec. So if we were looking at this mass spectrum for something we assume is a carboxylic acid, and based on the other information from our HNMR and our IR spec, we have a pretty good idea that this is propanoic acid. We're just going to confirm that using the mass spectrum. First thing we look at is the total molar mass of the compound, and that's found at that largest big peak, which is here, which is 74. So the molar mass of our compound is expected to be 74, and if we look at the molar mass for propanoic acid over here, we see that the molar mass is actually 74. So that works out. The peaks in the middle come from fragmentation. So we look at the peaks here at 28 or 29. They're both very high, so it could be either one. We have a peak at 45, and we also have a peak at 57. These come from fragmentation of the molecule, which happens with that electron beam. We can fragment the molecule with the electron beam here, and it creates both an ion and a free radical. This could have two possibilities. It could have an ion that is CH3+, which would have a mass of 15 showing up on our spectrum. And we do see a very small amount of that present there, but it's not very common. We could also, if that CH3 is created, we would create the free radical CH2COOH. Now, this would not be recorded because it doesn't have a charge. A second possibility for that same fragment would be to create the CH2COOH ion, which would have a mass of 59, which would show up on our mass spec. And again, we see a very small amount of that 59 ion. When that is created, we would also create the CH3, but it would not have a charge. It would be a free radical, and therefore it wouldn't show up on the spectra. Now, if we instead cut the molecule here, we would create a different set of ions and free radicals. Two possibilities also exist. We could create a C2H5 ion, which would have a mass of 29. This is what we're likely seeing over here. That mass of 29 shows that ion is actually quite abundant. Now, when we create that, we would also get the other side, free radical of COOH, and it wouldn't show up because it doesn't have a charge. We could also create that COOH ion, which would have a mass of 45, and we would have on the other side the C2H5 free radical, which wouldn't show up on our spectra. And look what we also see. We see a whole bunch of that 45 ion. Our last possibility would be to cut the fragment here. And so that would give me the ion C2H5CO, which would have a mass of 57, and I would also get the OH, which wouldn't show up. This is clearly evident here. We would also possibly get an OH ion, which would have a mass of 17, and then we would get the C2H5CO free radical that wouldn't show up. But we don't see that peak, and so that is very uncommon. The mass to charge ratio for us is fairly straightforward. Because we are using this electron beam to fragment a molecular compound that is neutral, we are always going to form a 1+ ion when the molecule breaks apart. So the electron beam comes and attacks this bond here, and it takes one of the two electrons that are in that bond with it. So we have 2 E- that are produced or removed, and then we have that single electron that is left here, this one, that attaches to either the C2H5 fragment or the COOH fragment, creating your free radical. Now, the one it doesn't attach to is the ion. So if it attaches to the COOH, we would have that C double bond OH free radical, and I would also get the C2H5, which would not have any electrons in that position, so it would actually have a 1+ charge. This gives me a mass, which is equal to 29, and the charge of +1, which gives me a mass to charge ratio of 29.